So today we will do chapter 9. So introduction to finite state machines. Actually, this is a short chapter somehow. And I think quite a number of the material inside this chapter is already been, you have experienced or you have learned it probably on your own by doing the milestone 4. Okay. So basically the content for this chapter is introduction to finite state machine. FSM stand for finite state machine modeling, and then the design of FSM. And then there are two type of FSM, which is more FSM and milli finite state machine. And then we compare more and milli. So now the general structure. In general, the finite state machine is actually nothing but a sequential circuit. It's just a sequential circuit. However, it is more in a structured way. So basically, it's still you have the two section of it. One is combinational logic part, and the other section is the memory part. Okay. So, however, the combinational logic part can be divided into two parts, which is one, the green color one here is for the output logic parts, which is pure combinational, and the next state logic part. And of course, you have the flip flops. And the flip flops have the next state and the present state. You have the external input, you have the external output. Sometimes system like counters, you may not have external inputs, and the state output here is the output itself. Now, so there are three main components that you have to know in the that comprise inside the finite state machine. One is defined as state memory. So in general, it has two type of and distinct states. Distinct means you cannot give names which is overlap. The names of each state must be unique. So n representations where n actually represent the number of flip flops. Okay, it can be the other way around. When we do analysis, we know the number of flip-flops and we figure out the type of n. But when we do design, we know the two type of n distinct states, and then we have to figure out what is the n, suitable n. Next is the next state logic. So normally we will use a symbol Q, capital Q, with the plus symbol on top of it to say this is a next state logic. Next state logic and present state logic basically is the same thing, except that where you read the data. And last but not least is the output logic, and this is something that you want to observe, something that you want to see from the whole finite state machine. So the output function, the output function is actually a function of current state and inputs. Okay, that is also depend on which type of model. So there are two models that we're going to use. Basically, is the milli model and the Moore model. Okay, so for the general structure of the Moore model, so we start with Moore. So for Moore model, you have the next state, you have the memory, and you have the output. However, as I mentioned in the milestone 4 class on Friday, more model, the output does not depend on the input. So the output only depends on the memory. In other words, for more, if you have the output F is only in terms of Q. Yeah? Q, if there are many Q, then how many Q? It not depends on the input. There's no input line that goes to the output. I mean, directly. Indirectly, of course, because input will interfere with or will decide on the register, but the output here is only taking from the register. So this is basically your present state. This is your present state, and this is your next state. Okay. And then next. Now, however, in the melee model, right, you will see the input here goes also to the output. So in other words, now your output not only depends on the present state, but also depend on the input. Eh? The output here depends on the inputs and the present state. Okay, so that is actually the big or the main difference or the main difference. But because of that, you will see the output here where it changes also somehow it will be different. Okay. Next, the timing. Now, as I mentioned before, timing is quite important. So you need to have clock. For asynchronous, for finite state machine, clock is a must. So you have a clock. So one complete pulse, meaning from 1 and 0, this is called state time. So usually we inspect output state by state time by state time. And the input, let's assume this is a positive triggered. If we assume, I mean, for all of our cases later on, we will assume positive age here. So when you assume positive age, your input should has to be ready prior to here. It's already ready by the time the clock coming, right? So this is your status of your input, and you can do some changes, which will not interfere with the output during the low level to be safe. And your output, you can say that the TCO is the time for that required for the output to settle. So in other words, these are kind of ambiguous output. The correct output is here, assuming there are some maybe propagation delay here. But when we do simulation, if you notice, we only do functional simulation. There are two types of simulation. One is functional, one is timing. So because we do not involve with the hardware, because we don't have the CPLD, we mostly doing the functional simulation, and therefore this situation mostly you don't see. You will see this one right over here, starting point. Yeah, and this one you see, but it doesn't interfere. In fact, if your input changes right on time here, it will take prior or right before. So this is the timing. So this is something that you have to be careful when you provide the input to the system. Now, this is a comparison. This is a comparison, a simple comparison of a state diagram. This is actually one of the flip-flop. I think this is a D flip-flop. Okay. Now, if you remember D flip-flop, I think this is a D flip-flop. Let me see. Okay. So the first one is called is more, right? For more, you have, of course, minimum you have two state. Now more, the input is sit inside the state, because if you remember, more only depend on the register output or the present output. Sorry, the present input. Sorry, present state. Okay, so therefore somehow this input, these are input, these are input, these are input. It will not interfere. By the way, remember the three components of the finite state machine. The state. So the state is this one. The circular symbol is the state. And when you put it A or B, that means you give the name for the state. Sometimes, in fact, in my case, normally standard I give S0, S1. I always start for S0, S1 for the state name. But sometimes it's nice to put it based on what function it is. Now, the line here is a transition. So that means this line can transition from A to B on the positive clock. So whatever transition here is only occurring at the positive clock. So the line here is the transition. And of course, why or how you transit from one state to another, it depends on the input. So this is the input, right? And for more, the output sit. So you can do either bar and then you write the output. Sometimes you just ignore this output. You don't put the 0, just highlight the 1, or you put the label. And for example, if the input is X, then you say here X, X bar, or just leave it, right? But when you come up with the truth table, you know when you don't you have, 0, I think you have to do it. Because if you don't have anything, meaning by default, it goes to this one without any issue. So 1 is your X, your input is 1. It will transition from state A to state B. If the input is 0, it stay in that state. If in now is in the B state, if you receive a 1, it will stay. But if you receive the 0, it will go to 8. So this is actually a D flip-flop. This is actually a D flip-flop. If you analyze, this is a D flip-flop because Q plus is equal to Q plus is equal to D value. Now on the second one, milli, on the other hand, your state is clear. Inside the state is just the state name or the state code. So your output lies during the transition. That is why your output not only depends on the state, but also on the input. Here, the output doesn't depend on the input. So here, what it means is that usually you have to say like X slash maybe F. F or whatever that you want to see for the output. So that means this one is X, this is the output. So that means here, if your input is 0, you won't trigger the output and you stay in A. If you are in the B, if you receive a 1, it stays in B and the output still not triggered. So it looks here, the output only triggered when you are from B state and you receive a 0. From B, receive to 0, it will go to A. And how many transition line that you have to do actually depend on how many input you have. So if you have single input, like this one, only one input, only one input, that means your from A, if the input is 1, go somewhere. If input is 0, go somewhere. If you have two input, for example, X, Y, then most likely you have 4 lines. But you can simplify the line by writing down the possibility of the input. Because the input is the 0, 0, where it goes, if 0, 1, where it goes, if 1, 0, and 1, 1. Yeah? And sometimes if you don't have anything on the transition, meaning regardless of the input 0 or 1, it will default to the next state. Okay, that's what it means. You have any question? You just you can voice out or you can highlight in the chat. Right. Okay. So then, what do you do then? Then you do the state table. State table is nothing but the state diagram, but state diagram in diagram format or picture, whereas the state table in table wise. So therefore, here you have A, B. So obviously here also have A, B, present state, next state, and then you have the input. Now don't be confused the A here with this A here. This is actually not a good choice because you may confuse the state A and the input A. But actually, this input is just another variable. That's A is another variable. It has nothing to do with this A. Okay? So what happened is that if your input, forget about the A here, if the input is 0, you go back to state A. If it's 1, go to B. Exactly as this one. So whatever that you have here, or something that missing here, you will clearly interpret it here. Okay? So similarly, if for now, the only different or obvious different between the more and the milli. More and milli is that for more, the output, for as long as you are in A state, for example, your output will always be 0 for both cases. For B state, the output will be 1. So that means the state, this is the line, state cover, the output only depend on the present state. However, in the milli, you have to figure out for all 4 possibility, 1, 2, 3, 4, because it not only depend on the present, but also the input, 0, 1. From A, if input is 0, 0. From A, if input is 1, 0. From B, if the input is 0, is 1. If from B, if the input is 1, 0. So that means you can have changes here. Whereas here, stay. There is a big difference. Therefore, actually, when you populating or you filling up the state table, for the more, you can just do the output as the last one, because more the output only depends on any of the state. For example, in the previous example, more the output is B state. So for B, that means B. So this is the B. So just for as long as the in present state is B, it always be 1. Okay. So you focus on the next state, input next state, and then you can fill up the output. This require practice for you to clearly understand this part. Now, right. In the previous one, you don't give any names to your state. Just use variable A or S0, S1, S0, S1. Okay? But that symbol here is already in binary. So again, we are talking about digital systems. We are talking about binary systems. Therefore, each of the state has to be given a binary numbers or binary code that represent the names or the coding for the state. So depending on how many state, for example, here only 2 state. If you use binary system to name this state, 1 bit is enough, because you can stay here, state for A equals 0 and the B equal 1. And it doesn't overlap if it's 2 state. This is where we say n is equal to 1. So 2 to the power of 1 is 2. Yeah. What is it just now? Here. N represent the number of flip-flop in 2 power of n. So if you have 2 power of m distinct, in this case, you have 2. So 2 is equal to 2 power of 1, therefore you need only 1 flip-flop if you use binary approach. I have to reserve that as well. Now, these are choices of encoding or naming the name of each state. You can use binary coding. So if you use 000, assumption is you have 3 flip-flop. You may also use gray code. Gray code is 0132675. You may use also Johnson counter. But frankly speaking, I never use Johnson. I did use sometime gray. You can use one hot method. This is quite often. It's just that to force this state to be 1, sometime you have to do asynchronous force with preset and clear, or you can use almost one hot method, whereby you create one more state, but this state 0, all zeros only occur once upon reset, and then the rest it will follow the sequence as this one. Okay. Now this is the design procedure. If you remember our course outline, we only assess PLO5, which is design. So obviously, you have to do a lot of design at system level, circuit level, but for digital systems, not just digital function. Okay. So now, for example, for the design procedure, you have 1, 2, 3, 4, 5, 6 steps. The first step is called conceptualize, which means you have to define in this process or in the first stage, you are given the problems or statements or whatever way of people giving you problems. But from that problems, you have to define all the inputs and outputs, and then you have to define system constraints. Constraints mean maybe certain like in vending machine, condition where both input activate at the same time is never to happen, never to occur, right? Or maybe the input is only BCD numbers. Therefore, numbers from, for example, if it's 4-bit, number from 1010 until 1111 will never appear. Once you define how many inputs and output, and then you give names for the input, for example, all inputs and output, then you come up with a state diagram. Now, state diagram will determine the number of state required by system, determine the required transition. So the state diagram is like we did before, because it is easier to realize or to transfer the concept into diagram before, rather than straight to table. But actually that depends. Let's say if you design a counter, a simple counter, probably you don't have to have the state diagram because you can easily go straight to state table, probably. And then the third, after you get the state diagram, now maybe you say S0, S1, S2, S3, blah, blah, blah. Then you have to assign code, suitable code. So either you want to use the binary coding, you want gray coding, or you want to do the one hot method or almost one hot method. So you assign. And then you use state table. But if you use one hot method, you don't use the state table. Yeah, you skip the state table, you can jump to equations. But if you use binary coding, gray coding, or the Johnson coding, you have to use the state table. And then from the state table, you create, no, from the state table, then you can come up with the equations. So inputs, if you combine present state and inputs, if is 4, altogether 4 variables. For example, you have to input D, N, and then you have state of S0, S1, S2, S3 that require 2 flip-flops or 2 variable. Still you manage to come up with the state table, but if it's more than 4 variable, then skip the binary encoding or the gray encoding, just go to one hot method. Yeah. And then of course once you have the equations, state table, after state table, normally you use K-map to get the equations. And once you get the equations, you can enter your design and verify the design. Okay, I'm not talking about Verilog programming, that is for different classes. So you use quarters to BDF. But actually, now that you know state editor, you can also from here you can start doing the state editor, but you still need to know the rest of the process. Okay, the editor is kind of cheating. Certain things they don't really show. Yeah. Now, for design procedure, basically, this is what we discussed before. So no need to go through this one. Now, let's start with the first example. This is actually you have done it in your milestone. So I think not much to say except that this is I think in your milestone you call it filter, right? Filter, I think. Now, this is like level to pass converter. If you remember here, for example, you have the one. This pulse, the width is 1, 2, 3, 4 pulses, long pulses. But you don't like to have the long pulses for the digital circuit. So you convert the long 4 pulses into only one pulse, and this pulse you transfer to your digital systems for processing. Yeah, you don't need all this wasting for. So this is basically the input that comes from human. That means from the switch, push button, or maybe from signal from transducer, right? Or maybe like a car parking system where you have sensor and the car stay there and it takes too much time staying there before pass through. But what importance is one car coming in, so only one pulse that need to be given in, right? So, or sometimes there are also cases whereby within the one pulse, you got a lot of jittering because the switch are basically mechanical structure. You press, but there might be some vibration or jittering. So you want to have a clean pulse. Yeah, so this is why level to pulse converter is quite important. So your first choice, you have asynchronous input from human, from your hand, or for example, so you can delay the signal using synchronizer. You use two D flip-flop. This basically delaying so that if you have 2 or 3 very fast input, only the first one capture, and then the first one transfer here. So once you get to the L, it will be clear rather than the messy input. It will be a nice pulse, nice structure here. No what do you call it, glitch or like rampant input, jittery input here. Okay. Now, this is how you visualize. So basically, this is your problem. You have a problem with human input from switches, whereby it may take longer or it may be not stable. So what you want to detect basically is just 0 to 1. This is called level to pass converter. Now, if you use more method, now level to 1, sorry, level to pass is basically 0 to 1. Oh, sorry, not nice. Okay. Basically, level to pulse. That means it could be like, okay, could be from level 0, assume this is level 0, going to 1. So this is your input, okay? However, at your output, you want it to be, as long as you see transition from 0 to 1, from 0 you go to 0. When you see 1, you want the pulse to be 1. You see this 0 1 transition, you want the output to be 1. Uh, how do I get the 1? Okay. And then when it level to 1, here, you want this pulse, the output, this is the output, to be 0, back to 0. I don't know how the pen, why the pen is not working, not here. Ah, I couldn't control the pen, although how many weeks already I work with this thing, right? So you want the output to be pulse. That's why you start from 0, and then when you detect the age, you want it to be 1. You want to be 1, and then regardless of what happened after this, either it goes down, or it goes, either it stay 1, or it goes down, right? Here, 1, I mean 1 is twice. You want the output to be forced to 0. That's why the transition when transition from, when you receive the 1 here, so the output from 0 going to 1, and then if you remain 1, you will force the output to be to 0. This is why you force the output to be 0. However, if right after this you got 0, that means you got 1, 0, 1, 0, like this is 1. That means 0, 1, 0, that is 0, 1, 0. You go back to 0. So if you do this process, you got one complete pulse at the output. Even if you go through this long process, that means you got 1 and another 1, still your output is still 0, 1, 0, but the 0 coming from here, 1 coming from here, and 0 coming from here. And then go back to this one. If you still got 1 again, that means you already have, in this situation, it's like you have 0, input 1, and then another 1, and then another 1, and then another 1, another 1, then suddenly 0. This is what happened from here. But your output still 0, 1, going 0. Like that. Right? Because the output inside is already 0. Here. This inside is already 0 regardless of how many times you turning around here. The input here many, many times, but the output is 0. But if you start receiving 0, here 0, then obviously if you see 0, next thing you expect is 1. So that's why it has to go back to the first, the 0 state, so that you can start looking for the rising edge. Okay, that's why you need the third one. This is for more. For more, normally this is like you detect 0, 1 actually, kind of like you detect two sequence. You have to detect 0 and 1. That's why you need 1, 2, and you need the third one to settle. Now, as for if you apply milli, no, okay, let me see. It doesn't go to milli yet. I need to erase. Actually, I have the whiteboard, but I need this screen as well. Now, if you looking at it, wait, why do we need 2 bits, Q1 and Q0? If you use binary, going back, you have 3 state. Now, if you have 3 state, then you have to give name to the state. Of course, you name it as 0, age, and 1. Now, if you use binary coding, the 0 here is you say 0, 0. Right? The age, you can name the age here as age here, name it as 0, 1. And the 1 here, name it as 0, 0, 0, 1, 1, 0. So you have 0, 0, 0, 1. In other words, because you have 3 state, you need 2 power of 2. You need 2 flip-flop. And you have this and this. This is why normally we do Q1, Q0. Let's standardize for our class throughout the semester. The present state and next state, always we use symbol Q, Q1 or Q0, unless otherwise specified. If default, we just use the Q. Okay. Now for next state, you do it like, for example, Q plus. That will be for next state. This is what present state, next state. Okay. We will standardize. And also, luckily, our coordinator have decided throughout the semester, how many weeks left? We only use, for our design, we will only use D flip-flop. Okay? We will only implement using D. D flip-flop. And if you remember D flip-flop, your Q plus is equal to D. Is equal to D. And therefore, you just need to do present state, input, next state. Yeah? Like this one. You need present state, input, next state, and indirectly, Q1 plus and Q0 plus is actually representing. Right, let me use a smaller pen. Actually, this Q1 is representing D1 for flip-flop D1, and the Q0 is actually representing input for flip-flop D0. Yeah, the reason is we use D flip-flop, and remember D flip-flop, D1 is Q1 plus and D0, Q1 plus is equal to D1 and Q0 plus equal to D0, or vice versa, D1 is equal to Q1 plus and D0 is D0 plus. So again, if you look at it from state 0, 0, if your input L is still 0, don't go anywhere. If your present state is here is 0, if you detect 1, input 1, it goes to the next state, which is 0, 1. We name it H just now, right? But the output is still 0 because output is single bit, output is based on here. The output is here. Output is based on this state, right? You remember just now? And then from state 1, if your L is 0, that means you haven't received anything, stay there, wait. If your input is 1, you go to the next state and you trigger your output to be 1. Right. Now when you are in the 0, 1, now this is actually not binary. Yeah? This is actually they use gray encoding. Because if you use binary encoding, after 0, 1, after 1, 2. This one is 3, so it's okay. This is the third stage, which is the 1 state. So once you're there, if you receive a 0, you set your output to 0. So you have the 0, you have set the output to 0. So 0, 1, 0. And at the same time, you return to the first state. But if you receive 1, just stay in the same state, but your output still going to 0. Eh? So this is direct translation from state diagram. Whatever you have in the state diagram is here. Whatever that is not in the state diagram, you have to figure out. Is it don't care or is it understood that it will be 0 or 1? Okay, that one you have to based on experience. Okay, then from there, from here, let me see. Right, from here, how many equations you will come up? Remember, from conceptual to state diagram to state encoding, to state table. Now you are going to the fifth level, which is the equation. So which equation you need? You need the equation for Q1 plus, equation for Q0 plus, and equation for P, because the equation is basically Boolean equation. So once you have Boolean equation, you already have, you know what logic to use. Okay, either and or not. Yeah, three or these three basics. Okay. Now again, this is three input, 1, 2, 3, and three output. Now, if you want to do K map, you have to imagine this one like truth table. So for truth table, you will divide into two column. One is the input and the output, right? Now for the K map. For the K map, you don't have present state, next state. So what happened is actually you have the input and you have the output. That means you need three K map, one for this, and one for P. But for P, usually it's very simple. I think you can do away with K map. You don't need K map because I think I can figure out from here P is equal to what? Suddenly. I didn't do that by accident. Now from here, actually, I know P is equal to P. P is P. P is equal to 0, 1, meaning L is not considered. So that means P is basically equal to Q1 bar and Q0. Okay? So you don't need K-map for P, only do for Q1 plus and Q0 plus. Don't waste time doing something which is not necessary. Okay? So next, this one is not needed. Okay? This is just to show. And this is actually to show that P doesn't have the L inside because P does not. This is more, remember? It doesn't depend on L. So you have like two variable K map and you have the Q plus equal to Q naught plus equal to L, and this is how you come up. Yeah? This is like revision. You have the X, the don't care. Why you have don't care? Yes, because remember, we have only three states. And because you use gray code just now, the state 1, 0, you use 0, 0 for 0, 0, 1 for age, 1, 1 for 1, but 1, 0 is not defined in the state diagram. So those state that is not defined, you give it as don't care so that you can simplify your equations. In this case, you don't use the don't care because that is good enough. But in this case, it's nice to have the don't care so that you have simpler equation. Okay, and then you implement. Now, where is it? P is equal to Q1 bar Q naught. So P is basically a logical combinational circuit. Q1, Q naught bar. So the P. So try also when you do your implementation using quarters, you put your state memory in the middle, your input state on the left, and the output state on the right. Okay. And also, but in your implementation, don't do the feedback here. Okay. Simplify it. This is very simple. It's okay. But when your circuit have like 4 or 5 flip-flop, this is messy. So the part of this one, you just label, this one you already label Q1, already label Q0. So over here, you can use the label of Q1 and Q0 without having this feedback. This one is okay, L. That's it. Okay. So you have this level 3, always have 3 layer. But I will, normally what I'll do on top here, I create, probably sometimes you have the Q1 bar or L bar, create that as well. Okay. Now, what is this? This is example. This is the same thing, right? This is alternative. Instead of use 0 or 1, but this is a bit trick, is it? Because L can be low. But here L is not low. L is the input. So you can also use this type of configure. You straight away give the state code. So you put the 00 code, 01 and 11. In fact, P equal 1, actually you don't have to say. You just say, you put a line and P. And then this one, if you don't put anything triggered, meaning understood 0. Yeah? And you say the L, which means 1, the L bar, which means 0, L bar means 0, L means 1. You can use the variable as well instead of the number. And in this case, I just put you example. We can also from here look at it. Let's say if you are from here 0, and then you still go 0, and then you go 1, and then you go 1, and then you stay 1, and then you go 0. I'm doing this one. Go 0 here, and then you go what? 0 again. So 0 again, meaning you are here. So let's trace the P. Actually, you can trace the S. That's why show the state as one of the output as well. State. This one, state 0, state 1, state 2, for example. You have the state as well below. I cannot do it. So look at it. When you see 0, 1 transition, the output will have 1. And then if you have 1, 1, 1, nothing will have the output. Now you check also, you see the 1, 0, 1 again. You have the output 1, nothing happened. Again, you see the age, the output is triggered. You see the age, the output is triggered. You see the age, the output is triggered. And this one also triggered because you see, but I didn't put it there. Yeah, I cannot put it there because this is what is this? This is a PDF. Okay. Now again, if you notice, if you use melee, you can reduce one state. And this one, if you reduce one state, meaning instead of using 2 flip-flop, you can use only 1 flip-flop because 0 can be denoted by just 0. 1 can be denoted by 1. So that means you require only 1 flip-flop. You need only 1 flip-flop. Okay? Now, can we take a break for 5 minutes? Do I have to leave because I got something to do? You check yourself. I stop recording. Pause. Okay, sorry about the interruption. Okay, so for melee, right? For melee, you can reduce one state, and actually, when you reduce one state, it's actually quite in this case, it's quite significant because instead of using 2 flip flop, you can only use 1 flip flop here, right? So when you use 1 flip flop, because you have only 2 state, so 2 state that means that require 2 to power of 1, so only 1 flip flop. So what happened is that when your input is 1, you have the output is here. The output is here. So output only trigger one time here. Okay. When you are in the 0 state, if you receive 0, that means you don't receive anything basically. You stay in that state. If you receive 1, you go to the 1, another state, and you trigger. At the same time, you trigger your output to be 1. And if you receive, if you receive another 1 input, now, this is like a prolonged input of 0, 1, 1, 1, 1. However, your output has to go down to 0, right? But if you receive a 0, obviously your output follow 0. So you got a simpler melee. And then, let's say, so if you name the melee as Q, because you only one flip flop, only one Q, and you don't have to say Q0, just say Q, and then your input is L. Your next state is Q plus. If you notice, if your current value is current state 0, if your input 0, stay, no change. If you are in current state, you receive a 1 and you change to state 1. I mean, you change your state value to 1 and also the output to be 1. Now you look at the output. Output not only depend on the state, but also the input. And if you are in the 1 state, if you receive 0, go back to 0 state. And your output, also you have to push down to 0. And if you are in 1 state, if you receive a 1, your output is still 0. And the state remain there. And you got equation Q plus equal to L, P is equal to Q bar L. I think this one no need for K-map. You get Q plus is equal to 0, 1, and 1, 1. That means L. Because Q and this one we cancel out. and the P is simply equal to Q bar L. Yeah, that's all. Q bar L. Okay, you don't need a key map if it's very simple as this. Don't waste your time. So this is your milli type, only one flip flop, the L. So the input basically there's no combinational logic required for the present state. It's simple enough, only for the output, and this is your P. And this is, but when you compare more versus milli, what can you see? Okay, your input has funny shape here. You got 0, 1, 0, 1, blah, 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 right? And then steady. This is like some jittering in the beginning here. So nothing happened here. Somebody press a button. If it's push button, maybe normally off button. Initially the button is 0, you press, but the process taking 2 plus 2 pulses before it steady. So for P machine or for P machine, for more machine or for more finite state machine, here it doesn't detect, right? And the state is still 0. And then this one is not recognized because it only recognized at the clock time. So during the clock now, this is 1. So 1, that means it goes to the edge because now it detects 0 and it detects 1. So the state, it goes to the second state. At the same time, the output is turned on. Now this delay is just the way of saying propagation delay. But when you do functional simulation, you don't see this delay. This delay is like hardware wise. Okay? Doctor, your voice is slow. Why am I slow? Am I still slow?
Okay, okay, doktor.
Okay dah? Okay, alright. Uh, it's okay now, eh? Alright, sorry, I think my microphone. And then now what? The thing is, the more has clean output, whereas the mealy, it will detect. Remember, mealy is depending not only the state, which is the 0 state at the moment, for example, but also the input. So as long as it's in 0 state, if the input is 1, it will go 1. If input is 0, it goes 0. If input is 1, it goes 1. The output changes, right? And then at that triggering point, then only it changes to 1 because what is the P? P stand for, wait, let me see, P is equal to Q bar L. Q bar L. P is equal to Q bar L. But here is like Q bar L. Not the Q, but the Q bar. The 0 one. So you are, here the Q is 1. Okay, we figure out this one. It copies, it copies the whole thing here. For as long as the P is equal to milli, P is equal to Q bar L. And what is Q bar? P is 1. For 0 state, 0, P is 0. If 0, 1. Here. As long as your Q is 0, here, your P, it will follow the L. 0, 1, 0, 1. So the same here. Your state is 0, which is the first state just now. So then your output equal depends on the L. That's why L0 is 0, L1, 1, L0, 0, L1, 1. But once you go to the next state, does it still follow? Let's see. If you are in this state, if 0 go to here, the output always 0. Again, if you are already in the 1 state, or when Q is 1, if the input is 1, you stay 0. If your input is 0, also stay 0. That's why here, if you are in this state, okay, it detect, if it's 1, it moves to this one. That is the transition between 0 to 1. And then once in this level, regardless of the input, right, it will stay here. If the input is 1, it stay in 1. You see the clock, the input stay 1, it remains 1. So the 1 here is longer because of the, actually what happened is that it stay here. right? Stay here. 1. And then if you got 0, P0, then only you got 0 here, then only transfer here. 0. But then again, for me, my personal view on this matter, I prefer more. Because more, the output is clean. Rather than milli, you have to be careful with your input. Milli, in this case, is not good. So how do you overcome this problem? And when you do the state editor, you have the choice of your output. It says you want to register the output or not registered. If you register the output, meaning the output will stay, for example, this first output will stay for the whole clock time. So that means you don't see this jittering. But if you do not register the output, that means what happens is that when you register, meaning right after this come out, it has another register just to hold the data. If you have the data, then you don't have that flickering here. It doesn't occur here. It doesn't change your output. That is more like modified MIDI. Okay, and this is it. So you have next state, you have output, and here the output register. This is what I'm saying. What I'm saying. So if you have milli and you want to avoid that not nice, the solution is you create an output register. Okay, and I think this is your application. This is like, remember the switch. This switch is a mechanical switch. So this is a filter. This is actually the filter. Filter here is actually combined of this level 2 pulse and also this one. This is level 2 pulse and also this synchronizer. Actually, you have to do this one, the edge detector plus the synchronizer to be nice. So you delay a little bit. Okay, that is actually for in electronics. As far as digital concerned, that means from here onwards, when it's digital, it's not an issue. This part is the issue of the switch. This prescaler, on the other hand, what is the issue? Your eyes cannot capture 50 megahertz. That's too fast, right? So because of too fast, you reduce to do 1 hertz, so you can see the changes here. However, when you take 1 hertz is 1 second. 1 second is what? I think it's quite a long time as well. 1 second between 1 second to another second. Like one, another one. 1 second, right? So if your hand is faster than 1 second, you will lose your signal here. If it's a push button is that when you touch and then you let go of your hand, it will let go. So if you use 1 hertz, maybe during the before the 1 hertz coming, you already lost your signal. That's why suggested you increase the frequency here to 100 hertz to able to catch your human behavior. Because I think as I'm speaking now, obviously I'm talking from one syllable to another syllable is faster than 1 second. Same as your fingers. I think you can move your fingers faster than 1 second. That's why you put 100 hertz, which is 0.01 second. I don't think you can beat that 0.01 second, and therefore the input filter can capture that. That's why you change the frequency here, is to enable to pick up if you are too fast compared to the 1 hertz. Yeah? But the rest of the clock here has to be 1 hertz. Now, because of our MCO situation, which means what happened? I think some of you bring back your CPLD or some of you is in UTM, but just to standardize for everyone, you don't need to do the hardware. So which are the hardware part? Obviously the switching part. Obviously the filter part you don't need anymore, but you can do it, but a simpler one. Maybe you can do the edge detector part, but not the delay part, just the edge detecting part for the filter. And obviously the selector, I think it will select either you input the D or the N, right? So maybe the D for dime, N for nickel. If in US style, N is 5 and D for 10. The prescaler you don't need anymore. You just get the clock straight from your simulation clock. The display here you don't need, but you can just use BCD. Yeah, this is like 5-bit output, but this one is just you group this one into BCD. If you can group both into BCD is better, but I think it's not possible to group this one so that you can see in binary, or when you do quarters, this one will appear as either 0 or 1, and this one in the decimal. Yeah? So this is just display. You don't need, uh, actually this is BCD. Actually for this one you need 7447, or you need the BCD to 7 segment. So you skip that part. The Night Rider part, I think it will be nice if you can use it. You can do it. But the Night Rider is possible only, I think, once you detect, you have to finish the Night Rider before you can accept new data. Otherwise, your Night Rider cannot finish the sequence if you're too fast on this one. Right? So that means there should be some done here only, clear. So the done here is to tell you that once you finish the Night Rider, then only you can accept new data. Otherwise, your Night Rider will play halfway crossbeam if your input coming too fast. All right. So I think you have until what, 28? I don't remember the due date for your milestone 4. So show me that in terms of demo. So demo, I think you can do something like what I'm doing for your demo, could be. But in your output, don't just show one possibility, perhaps minimum three sample input, including sample of when you don't receive the input, if you don't receive the input. Yeah, I think, and that's all for today. I can stop the recorder, stop, and then I can pause, or can stop sharing as well. No, right? And yeah, I can stop sharing.